Welcome to Chemistry 111. So today we'll start by looking at both Chapter 7 homework and Lab 4, which technically won't start for like another, we won't be doing Lab 4 for like another week or two after spring break. But really, Lab 4 is not something that it's supposed to be very hard. It's a lot of very good practice work on Chapter 6 and Chapter 7. So if you get started on that early, you could actually use the lab time to get help on homework or something else. Because this Lab 4, very good practice for the upcoming test, which we'll have a week or two after spring break. So, okay, so we're going to start by looking at some of the homework. Now, please note, there is some homework technically due over spring break, but it's assessment, so it's not like a set due date. Just try to go on track. You do it a little bit late, that's not going to be a big problem. Okay, looking at this, just looking at the problem sets, there's only 13 questions on Chapter 7, the main assessment. Just looking at the types of problems. So the first set of problems all has to do with determining what is the molecular shape. So when we see molecular shape, we're going to think molecular geometry. There we have the electronic geometry or the molecular geometry. The electronic geometry looks at just the number of things coming off of it. The molecular geometry or molecular shape looks at the number, differentiates between our lone pairs and our bonds. Please remember that a single bond and a double bond both just count as one thing coming off. So let's do at least one or two of these problems because we'll have plenty of chances to do these, look more at these problems when we have go through some of the lab. So what is the molecular geometry of ammonia? We look at how many electron domains we have. 1, 2, 3, 4. How many of them are lone pairs and how many are bonds? We have 3 bonds, 1, 2, 3, 1 lone pair. So the electron geometry is for 4, which is tetrahedral. However, the molecular geometry is for 4 electron domains, 1 lone pair, which is trigonal pyramidal. Now, if that is not obviously something that jumps to your mind, that's where this lab that we're going to go over in a little bit will help doing this. There's a nice little chart. You can look through this and you'll be good. Ammonia, just like ammonia, ammonium, just like ammonia, has 4 electron domains. The chief difference here being that 4 bonds, 0 lone pairs. 4 electron domains, 0 lone pairs is tetrahedral. BF2, BEF2, beryllium fluoride, 1, 2 things coming off of it, so it is linear. But SH2, 1, 2, 3, 4 things coming off of it. 4 electron domains, 2 lone pairs. 4 electron domains puts it at tetrahedral. 2 lone pairs puts it at bent. This one is just trying to show you that the difference between electron domains and molecular molecules, and the difference right here between, well, I've drawn this linear in both cases, but is this actually linear? No, that's actually bent. So gonna skip around maybe a bit. So this one, they want you to put the electron pair geometry and the molecular geometry, just like we did. So this will be just like the lab we're going to do. You find the electron domains, and that'll give you the pair. Then you find the molecular geometry based on how many lone pairs there are. Sometimes these will be the same. Sometimes they'll be the same. Oftentimes they will be different. But if there's no lone pairs, they will be the same. Skipping around. Finding, the molecular geometry of individual atoms. So just looking at, like, say, in this nitrogen, you have 1, 2, 3, 4 electron domains, 1 lone pair. So it would be a trigonal pyramidal atom. 1, 2, 3, 4 electron domains on the carbon. So it would be a tetrahedral atom. 1, 2, 3, and just so on. You can do each individual atom and look how it all fits together. Yeah, more of the same. Given the formula, blah, blah, blah. What is the shape? More of the same. Okay, this is our first thing that's going to be really kind of tricky. Which of these molecules are polar? Which of these molecules are polar? Though, let's draw this out. So we need, and they draw them out for us. Let's see. CHHCl. But these Lewis structures do not give a good approximation. PCl3. Okay, we have SO2 and CO2. Okay. Now, to be polar, we need both a polar bond and a polar shape. Now, drawing them as Lewis structures, you can't really get the shape because the Lewis structure is just whatever was convenient to draw as long as it was valid. The polar molecule, let me bring this close. The polar molecule, we actually have to use a little bit of VSEPR. Now, fortunately, all these bonds are polar. This is a polar bond. This is a polar bond. This is a polar bond. This is a polar. All these are going to be considered polar bonds. However, we have to look at the shape. When equal and opposite, they cancel out. Equal and opposite, they cancel out. So the degree of symmetry in the molecule will determine whether this is polar or not. And this is why Lewis structures by themselves will not always tell us. Looking at CO2, 2 things coming off the carbon, the shape of this guy would literally be linear. This makes this very, very symmetrical. Symmetrical through here, symmetrical through there. We can fully rotate this 180 degrees that way. You could rotate this any amount of degrees that way. Basically, this cancels this. 1 oxygen on the right cancels 1 oxygen on the left. In this case, the molecular geometry is linear. The electronic geometry is linear. Those 2 things are the same. This guy's not going to be polar. Now, this guy, SO2, we notice we have a lone pair. When we draw this guy, it would actually look like that. It would be bent. It would have a trig planar electron geometry, but bent molecular geometry. Drawing it like this, it looks like they would cancel out. But drawing it like its true VSEPR model, we see this oxygen and this oxygen both pull down. So we have a net dipole of down between the two oxygens. Hint is all the atoms are the same and the electron geometry and the molecular geometry are the same. It cannot be polar. But if they're different, there is a good chance that it might be polar if these are different. Looking at PCl3, this one still looks polar no matter how you draw it. Like this, it looks like, well, this guy is polar. But truthfully, this has 1, 2, 3, 4 things coming off of it. So that's going to be a tetrahedral shape. So drawing it like it should be drawn. We have right here chlorine pulling down left, this guy pulling down front right, that guy pulling down front, down back right. The net pull is straight down through this molecule. This guy would be tetrahedral trig pyramid. They're different. So this guy's definitely polar. But this last one, dichloromethane, drawing it like this looks like this cancels that, and this cancels that. But if we actually draw this in the tetrahedral format, what do we find out? If I draw it like this, no matter how I draw this, no matter where I put these chlorines, there is no way I can draw this structure so that this chlorine cancels that chlorine. This is a case where both electron geometry and molecular geometry are the same, but it's not polar. But it is polar, And the reasoning behind this is Cl is different H. These H's are weaker than Cl. So Cl has a net attraction up to the right. This guy's pulling front. This guy's pulling back. Both of them are pulling down. So we have a net attraction of down and to the right through those chlorines. No matter how I draw this, there is no way to avoid that. But you really have to draw them. You can't just trust the Lewis structure they decide to give you. So in this case, all except for CO2 are polar. And the only reason these wouldn't be is if you had to actually check the bonds and they were too small of a difference. Now this one, the next one, number 7, asks you, are the bonds polar? Are the molecule polar? Now it's possible to have polar bonds in a nonpolar molecule. But if you do not have bonds, you can't have a polar molecule. So if one is nonpolar, then the second one is nonpolar. But if one is polar, it can still be nonpolar if they cancel out. So you got to draw the actual Lewis structure, you draw the actual VSEPR model, and then say, do the two chlorides cancel out? Do the two hydrogens cancel out? So you actually have to look at that. Now I'm going to skip that, but that's essentially more the same. That one you can actually just hypothetically you should be able to get it. For God's sake. Okay. Thinking. There we go. Okay. 8. Draw the Lewis structure, including lone pairs. Then what is the molecular shape of this? What is the bond angle? And then you say, is this the single BF bond polar? Is the overall molecule polar? Now, what is the actual bond angle? We can use a little chart for that. Here's our nice little chart, which will come up in the lab. Typically, 109.5 is a tetrahedral shape. 120 is a trigonal planar. 180 is the linear. And then less than 109.5 would be something that would deal with trigonal pyramidal or bent. Now, why can't we put an actual number on that? That has to do with what the bonds are, what the elements are. We can't predict the exact bond angle. This one, hybridization. A hypothetical molecule where they say we can have some mixture of bonds and lone pairs represented by this. This structure, X is the center atom, YY with two lone pairs would be represented of X, Y2, Z2. And so what you're trying to do is figure out how many things are on the atom and thus how much the hybridization would be. How many hybrid molecules would you have? So my glasses are fogging up a little bit. You need at least as many hybrid orbitals as there are bonds. At least as many hybrid orbitals as there are bonds, and also often as many hybrid orbitals as there are lone pairs. So please note, for example, sp hybrid orbitals. sp, this one would definitely be sp, x, y2. There's only two things coming off the x. So we only need two orbitals. sp2 would be three things coming off the x. And sp3, that's four things coming off the s. That could be all bonds, like in this case, but it could also be three bonds and one lone pair, for example. And so you have to classify these guys based on how many things are attached to the X. It's kind of a weird question, but it's busy. If each lone pair is electron domain, each bond is electron domain, how many lone pairs and bonds? How many total electron domains? This one is just draw the Lewis structure. What is the shape? What is the hybridization of the center atom? What is the bond angle? And is this guy polar or nonpolar? Basically, that question is just like a question we're going to see in lab. So I'm going to just move on. This one's a little tricky. Don't screw this up too much. You can reset it. But basically, all this wants you to do is put lone pairs on the molecule. How do we do this? How do we know where the lone pairs go? The easiest way to put the lone pairs on is count the number of things you see coming off the atoms. How many bonds do you see coming off the atoms? Remember, carbon has 4 valence electrons. It wants 4 bonds. Nitrogen should have 5 valence electrons. So depending on how many things you see coming off the atom, you need to add electrons until it has 5. Oxygen should have 6. Add electrons until it has 6. And that'll be the safest thing you can do. This one, sigma and pi bonds. Remember, a double bond counts as 1 sigma and 1 pi, and a triple bond counts as 1 sigma, 2 pi. So you count all the bonds once to give you all the sigma, and then you count all the double and triple bonds as a pi or 2 pi and add those up. Easy peasy. And then one more just like that. Okay. Just wanted to go through this to show you. This is what I know last class period was molecular orbitals. Kind of tricky. But none of that's actually asked on the homework. So, okay, so this is the lab 4 that we won't be doing right away, but we'll be doing this eventually. I don't feel like absolutely assigning this over spring break, so you're more than welcome to work ahead because it'll be great practice for the test, but it's not due for quite a while. There's a whole lot of stuff explaining bonding versus non-bonding, molecular electronic. We talked about all this in class. The main things you will need, besides obviously work through the pre-lab, is hybridization. You will need this tiny little table too. That's just a quick reminder. If you count your electron domains, that will give you your hybridization. Electron domains will give you your hybridization. And you'll need this little page. This right here is a Pauling electronegativity table. There's different tables depending on what you want, but this allows you to compare the strength of bonds. So there's fluorine is 4, oxygen is 3.5, nitrogen is 3, carbon is 2.5. The reason I give you the hard limit is if the bond difference is between 0.5 or greater, it's polar. What is the difference between carbon and nitrogen? 0.5. What is the difference between carbon and hydrogen? 2.1 and 2.5, 0.4. So is a carbon-hydrogen bond polar? No. Is a carbon-nitrogen bond polar? Yes. Just barely, but yes. Is a nitrogen-oxygen bond polar? Yes. Is the oxygen-fluorine bond polar? Yes. And then here's the magical chart that I used several times in our notes. I got it from here. What we see here is the steric number on the left is essentially the saying what is the electron domain geometry. And the basic geometry talks about the bond angle and what is the electron domain geometry. And then moving your way across is the number of lone pairs. So if there's one lone pair, trigonal planar gets moved to the molecular geometry of bent and has this bond angle. Tetrahedral goes to trigonal pyramidal and then bent. Trigonal bipyramidal goes to sawhorse, T-shaped, linear. So, and let's just look at. So, okay, so what you'll do is you'll first draw a valid Lewis structure. Draw a valid Lewis structure. Determine the number of electron domains, the number of bonding domains, and the number of lone pairs. Please note, the bonding domains and lone pairs should add up to your number of electron domains. Then we'll get the ideal bond angle and the actual bond angle. You can get those directly from that chart. Get them directly from the chart. Trigonal planar, or the electron geometry, or the molecular geometry, get them both. Get them from that chart. Draw the structure. Then it's like draw the structure with 3D structure and put a dipole if possible. Is it polar? Yes or no? And then what is the hybridization? And then there's just from there like 10 pages of examples, 4 examples to a page. So I'm going to do like maybe 2 examples real quick from there. So I'll do 1A real quick. 1A, NO2 1 minus. So let's draw in the Lewis structure. Let's draw the Lewis structure of this guy. Okay. Now I can do this, the rest of the stuff by heart, but NO2 1 minus. N is 5. O is 6. There's 2 O's and then 1 electron. So we have 18 electrons to deal with. N comes first. I put in the center. 2 O's coming off of it. Perfect. That uses up 4. We're at 14. We put lone pairs around it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 2 electrons left. They go on the nitrogen. Now, nitrogen has 2, 4, 6 electrons. We're going to make a double bond. Now we have a valence structure that we've used up all of our electrons. Now for a question, is there more than one resonance structure we could draw? Yes. We are doing it like this in this particular case, but we could also do it like this. Put the double bond on the right, on the left instead of the right. This will not change your structure. Okay. How many electron domains? 1, 2, 3. So 3 enes. 2 bonds, 1 lone pair. Ideal bond angle. 1, 2, 3. So this is going to be 1. Going to be trigonal planar. Those 2 things go together because of the nature of trigonal planar. Ideal, that's the ideal. That's the perfect thing. But because it has 2 bonds, 1 lone pair, the actual number is going to be less than 120. And because of that, it's going to be bent. Once again, where am I getting that less than 120? Straight from the table. I happen to remember it. I've seen the table enough times. But so that's your basic things that this part you definitely shouldn't be getting wrong. If you get this wrong, you drew a wrong Lewis structure or you're really confused. And doing this before the test will help us figure out how to avoid being really confused on the test. Now, is this polar? We look at this structure. The trigonal planar bent structure. N and O are this. The difference here is 0.5. So is this a polar bond? Yes. Is this a polar molecule? Yes. The net dipole is straight between the oxygens. Straight between the oxygens. Right opposite of that lone pair. And then finally, what is the hybridization of this guy? 1, 2, 3 things, 3 electron domains means it has to be sp2. All that comes from our handy dandy little table. Little tables as a help, as assistance. So let's go back, find another one. I'm going to jump around to a different page. Oh, come on. Okay, let's go. And I want to just be able to show you something. Okay. One sec. So some of these, there'll be series, like some of these guys can be a page of tetrahedral structures, or it's going to be a page of trigonal bipyramidal structures. I want to show you something like CL. Let's see. I figure out one where I'll do radon tetrachloride. Well, now I'm trying to figure out one I could think. Show you. Oh, two more, and then in the class we'll go ahead and do radon tetrachloride and xenon trifluoride, like ion, radon tetrachloride. We'll do that one, and then we'll do NCS 1 minus. NCS 1 minus. Okay. Just to show you something very interesting, and that's where we'll stop at least going over this. Okay. Radon tetrachloride. Radon, it's a noble gas. Holy crap, we're making bonds to a noble gas. It's allowed to do that. We'll be fine. It takes some crazy conditions to do it, but we can do it. 7 plus 7 plus 7 plus 7. So 14, 28, 28, 36. We have 36 electrons here. Radon, I'm going to put in the center. I'm going to put a chloride. We're going to put a chloride. We're going to put a chloride. We're going to put a chloride. That's 8. Down to 28. We're going to put 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We used all but 4 electrons to give octets to the chlorine. The rule says we have extra electrons left. We slam them on the center atom. That's fine. Are we allowed to do that? Well, radon is like row 6 or something, I'd like to say. So yeah, it can hold extra electrons. 3, 4, 5, 6. So 6 electron domains. 4 of them are bonds. 2 are lone pairs. 4 plus 2 adds up to 6. Because of the structure here, I remember that 4 bond, the 6 electron domains would be 90 degrees, and it would be octahedral. Four bonds, 2 lone pairs, still 90 degrees, but be square planar. Now, redrawing this structure, square planar looks like this. Wedges and dashes to show 3 dimensions. Now, the question here is this a polar bond? Yes. All the radon chlorides are polar bonds. Is this a polar molecule? The answer is no. It's non-polar. Why? Even though all these bonds are polar, you can see this guy cancels that guy. They're opposite of each other. This guy cancels that guy. They're opposite of each other. Because of the nature of square planar, each chloride cancels the other chloride. So we have no net dipole, even though each bond is polar. And then finally, hybridization. 1, 2, 3, 4, 5, 6. 6 has to be sp3d2. And that's for all octahedral structures. Now I'm going to redraw NCS1 minus down here. One thing I want to show you on this one is just that it doesn't matter how you do the Lewis structure. You will still be fine. 5 plus 4 plus 6 plus 1. You have 6. Now you put carbon in the center. You put a nitrogen. You put a sulfur. We're down to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All electrons are used up. Now here's the sketchy part. Do I take a lone pair from the sulfur and a lone pair from the nitrogen to make 2 double bonds? Do I take 2 from the sulfur to the carbon? Or do I take 2 pairs from the nitrogen to the carbon and make a triple bond? It don't matter. You can draw this structure, and it will be valid. You can draw this structure, and you'll get the same answer. So we'll look, because we're only looking at the shape of the center atom. So let's look at here. In this structure, we have 2 things coming off the carbon. 2 things is 2 electron domains, 2 bonds, 0 lone pairs. How about this guy? 2 things coming off the carbon. 2 electron domains, 2 bonds, 0 lone pairs. It don't matter how you make these double bonds, you will get the same VSEPR model. It don't matter where you put the formal charges, or if you put formal charges, is the VSEPR model should stay the same. So you can do it linear. It's 180, it's 180. It's linear in both cases. But the question is it polar? Well, N, it doesn't really matter how we draw this, N and S. This difference is 0.5. This difference is 0. So is this polar? Yes, the nitrogen and carbon is a polar. So it's going to pull towards the nitrogen. So is it polar? Yes. What is the hybridization on the carbon? 2 electron domains. It is sp hybridized. That is essentially the lab. A lot of practice just like that. If you can do that, you're in good shape. We will go ahead and stop for today right here, rather than start chapter 8. In the meantime, look at this lab, catch up on the homework, try to get on top of things. Don't forget to be doing online labs. Do at least one online lab so they don't sneak up on you. They're not too hard. I've gotten a couple of them from one group of people, but really a couple of them from just 2 people. And the videos are only like a few minutes, like 2-3 minutes. So they're not super hard. Take a chance, do something useful. But okay, we'll start chapter 8 when we get back from break.